All right, let's look at some chapter 3, section 2. So now we're getting into talking about variation. Um, we're going to look at some how to use StatCrunch to do some of these calculations. And then we're even going to look at some of the text for this section. So let's look at number 4. And number 4, I believe, is just asking some of the basic questions. So the sample variance and the sample standard deviation. So if we're looking at this one, S squared is my sample variance, and then the next question would probably be what is S, which is my standard deviation. Again, there's a formula to do this. If you would like to, you can use the formula. I'd rather know what the standard deviation stands for. So I'm going to find it real quick. So I want the sample variance and standard deviation. So there's my variance and there's my standard deviation. Now this is just talking about how much my numbers vary. Let's look at something. If I had some numbers like 8, 8, and 8, and then I had 5, 8, and 11, and I had 0, 7, and 17. So if I was looking at the mean of these numbers, we could do that real quick. Do a summary steps of columns and 3, 4, and 5, and I just want to know what the mean is. Well, the means are all 8, but I have different data, right? And obviously different data. So what standard deviation tells us is how much it differs from the mean. The mean of these are all 8. So how much does it differ, these numbers differ from 8? Not very little, right? You would maybe think they don't. So let's just kind of see what our standard deviations are for these 3 columns. So standard deviation for these 3 columns. Well, the first one is 0 because there is no difference from the mean. Here the difference is 3 up and down. And here, again, the mean was 8, but my standard deviation is 8.544. So again, standard deviation is just talking about how much do we differ from the mean. And variance is another way to talk about how we vary. But typically we talk in standard deviation. Most people in the mathematical world and what we use things for is standard deviation. Let's look at another problem. I had number 8 listed, so we'll eyeball it. And now they're looking for the population standard deviation. So if we download our data, right, and we can do again stat, summary stats, columns. So we're looking at pulse. What this is our standard deviation. That's if sample standard deviation. That's if we had a sample. There's one down here which is called our unadjusted standard deviation. This one is the same thing as the population standard deviation. So if you're ever looking for sigma, the symbol that they used over here, it's looking for your population standard deviation. So this is standard deviation, sample standard deviation. This is population standard deviation. And it doesn't differ tremendously, but enough to get an answer wrong. So whenever you see this symbol, this is sigma. So when you see a Greek letter like mu for the mean, that means you're looking at a population. So this is our population standard deviation. And on StatCrunch, it's at unadjusted standard deviation. So please be aware of that. Also wanted to look at number 11. Because number 11 gets us talking about the empirical rule. We're looking at the 68, 95, 99.7 rule. And so in the book, they talk about that here. And they say that between plus or minus 1 standard deviation, we have 68%. Plus or minus 2 standard deviations, that would give us more of our population is 95, and plus or minus 3 standard deviations is 99.7. So a way that we can visualize that, we can do that in StatCrunch, but let's get back and look at the problem for a second. So what percentage of people have an IQ score between 88 and 112? Well, that's 1 below and 1 above. So between should be that 68%, as it states in the book. 68%. When we're looking at greater than or less than 88 or greater than 112, so that's less than 1 standard deviation or greater than 1 standard deviation. If I know the middle is 68, how much is everything else if this has to total 100%? So we would do 100% minus the 68%. And that one would give us a 32%. Greater than 136, so now we're even breaking it up more. So that would be 3 standard deviations. If a standard deviation is 12, and that means 100, so we'd be 1 standard deviation, that's 112, 124, 136. We just want to know how much to the right. So if we're just looking at how much to the right, I know that between here and here is 99.7, which does mean that there's 0.15% on both sides. So if I'm just looking greater, that means it's 0.15% of the population would be greater than 3 standard deviations. And that's what that question's asking. Greater than 136. So that's just using the empirical rule, using that table. The next question, I believe we are looking at Chebyshevs. Kind of sounds like Chevy Chase. In the text they talk about Chebyshev, and it has this nice little formula. 1 minus 1 over k squared times 100%. This is for any data set or distribution. The empirical rule, this is just for one of these nice normal curves, right? Oh, isn't that beautiful? Couldn't they all be unimodal and symmetric? But they're not, because that's not real data. We find out later that we can use a normal model for a lot of things, but if we do not have something that's symmetric, this will give us an idea. 1 minus 1 over k squared, where k is the number of standard deviations from the mean. So if we had any distribution and it was 2 standard deviations, plus or minus 2 standard deviations, that means k would be 2. So I'd have 1 minus 1/4. If I squared 2, I have a 4. So that gives me 3/4. 3/4 times 100 is 75%. So on a Chebyshevs, if I was plus or minus 2 standard deviations, I would be, I know 75% of my data falls between plus or minus 2 for any distribution. Whereas on the normal, on one of these nice, beautiful symmetrics, if I'm plus or minus 2 standard deviations, I'm 95%. So we're going to be, we can generalize with a Chebyshevs if we have no clue about the shape of the distribution. But if we know the distribution, we know it's symmetric and unimodal, and it follows this normal bell curve, we know 95%. So that's kind of the difference between the empirical rule and Chebyshevs rule, is that all I know is that it's at least 75% of the data lie between. So this is for any data set. It doesn't have to be normal. So that gives you the idea of how to do a Chebyshevs problem.